Hey and welcome back to part 2 of our series on cybersecurity. In this video we will get into encryption. I want to talk about the basic terminology and show you an example called the Caesar Cipher. The goal will be to understand the basic concepts and to break the Caesar Cipher in the end. Our first big hack. So without further ado, let's start with the video. As a starting point, what does encryption actually mean? The Cambridge Dictionary says, encryption is the process of changing electronic information or signals into a secret code that people cannot understand or use without special equipment. Bruh. Thanks for nothing. I think we should rather take a look at an easy example called the Caesar Cipher. It is actually a historic example because Caesar himself used it to encrypt the messages for the military. So how does it work? First, we need two things: our translation table at the top and a message to encrypt. Put some chicken on my greens. Now we think of a number somewhere between 0 and 25. This number is our secret and we only tell it to people who should be able to read the message. Since it is said that Caesar used the number 3 back then, we use it also for our example. So we take our number 3 and shift the whole alphabet 3 letters to the right. This is why some call it also the Caesar shift cipher. After the shifting is done, you can see X, Y and Z have no matching letter. Hence, we move them to the beginning. You could imagine the alphabet as an ongoing circle which starts over after the Z with the A. As a result, we have now a different way to represent our letters. A is now a D, B is now an E, C is now an F, and so on. The rest is easy. We have to check the new letter representation for each letter in our message and just apply it. You look up P and you see now it is an S and write it down. You can pause the video and try to reproduce the encrypted text on the bottom right if you like. You maybe noticed something already. If you have the same letters multiple times in the original, you will see also their translation multiple times in the encrypted version. For example, all the E's in the message are now displayed as H in the encrypted version. That's why we call it mono-alphabetic substitution. You substitute the same original letters by the same encryption letters every time. If the E's would be translated as different letters, we would call it poly-alphabetic substitution. Okay, but that's only a short fun fact. Let's get back to topic and try to get our original message back from the encrypted version. In the Caesar Cipher, you decrypt by just doing the opposite than for encryption. Imagine you are the receiver of our encrypted text. If the sender shifted the alphabet 3 positions to the right, you now shifted 3 positions to the left. Then you put the letters with no matching at the end of the list and you have the completed decryption table. Now you just follow the same process you already did during the encryption and get your text back. Put some chicken on my greens. And that's the whole magic. Now let's take a look at the concept of encryption in general. We are going to try to match the elements of the common terminology with the example we just played through. The plain text on the left is our original message, put some chicken on my greens. Then we apply some kind of encryption algorithm to it. In our example case, we use the Caesar Cipher. So we could describe the algorithm as each letter is replaced by another letter, which is a number of positions up the alphabet. This fixed number is our key, which was defined as 3. The result of the encryption is now the ciphertext, which is our encrypted plain text. To get back to the plain text, we have to apply a decryption algorithm, which also uses our key 3. The decryption algorithm is described as each letter is replaced by another letter, which is the same number of positions down the alphabet. And as a result, we get our plain text back. This chain of events from original plain text back to the plain text in the end must hold, and we call this the formal correctness of an encryption scheme. To take a look at the formal correctness in detail, we use two functions to formalize the encryption scheme. The abbreviation ENC stands for our encryption function, which takes our message and the key as inputs and outputs the resulting ciphertext. Following the same logic, DEC is our decryption function, with key and ciphertext as input and the message as output. Therefore, formal correctness means an encryption algorithm is correct if for all messages M and for all keys K holds if we encrypt a message M with our key K, which is written as ENC KM, and then decrypt the result with the same key K, we get back our message M. You can pause the video once again and try to understand the chain of events you see here. There's one last thing we should talk about. Maybe you ask yourself, how can I trust encryption algorithms which are described all over the internet? But that's okay. The encryption algorithms as well as the decryption algorithms are public knowledge. There's nothing secret about them. The only thing secret is the key. If you would encrypt a message by using the Caesar Cipher, you would tell the key to nobody other than the person who should receive your message. And this makes totally sense, because it is so much easier to tell your communication partner a simple key, such as 3, instead of explaining a whole encryption scheme. In fact, it makes so much sense that we call this the Kerckhoff principle. A cryptographic system should be secure even if everything about the system except the secret key is public knowledge. Because we could think of a new key for all our communication partners, but it would be very hard to create a new encryption scheme that often. Everything else is called security by obscurity, and we don't want that. So thanks Kerckhoff. And that's it. If that's it, we would have a huge problem, because the Caesar Cipher is super easy to break and not secure at all. I can show you in a minute how we could get the original plaintext from our example. One approach would of course be to just try all 26 possible keys until we get a proper text. But what about a hypothetical situation where we only could try once? What would be your best guess? In cryptanalysis, we try to find some patterns in ciphertexts even though they look completely random at first. In our Caesar Cipher example, we know that each plaintext character is always the same ciphertext character. Mono-alphabetic substitution as mentioned before. Maybe this could help us. So let's take a look at some statistics. If we know that the plaintext is probably in English, we could check which characters are used the most in the English language. This graph shows it's the E. Now we should take a closer look at the ciphertext. Are there characters which occur more often than others? If this is the case, we could assume that one of these characters is probably the encrypted version of the character E. So we count the occurrences for each and notice H is occurring the most. If we would have only one guess, it definitely would be reasonable to assume the H in the ciphertext is the E in the original. That means the key must be 3. So we apply the 3 to the decryption algorithm and get put some chicken on my greens. Seems like an English sentence, so everything worked out. I know the Caesar Cipher was a very easy introduction to cryptanalysis, but this is still warm-up. The most important thing is to understand the idea of finding patterns in the ciphertext. They mostly look like random sequences of characters, but if you look closer, you might find something. That's it for this video. I hope you've understood what encryption is about and could follow along the parts about formal correctness and Kerckhoff's principle. In the next video, we want to take a look at the Vigenère cipher, another historic encryption scheme, but a bit more secure than the Caesar Cipher. So, see you there.